Hello everyone! In this video, I'm gonna explain how to obtain engineering and true stress-strain curves from a simple tensile test. So let's get started. One of the most common mechanical tests is the tensile test. This test can be used to obtain a number of mechanical properties of a material. These properties can be then used in mechanical design of components and structures. In the tensile test, a specimen is pulled usually up to fracture or failure. The specimen is fixed at the bottom by means of a clamp. A tensile load, F, is applied gradually along the vertical axis of the specimen. The force results from an imposed displacement that is controlled by the operator. So basically, the operator can set beforehand the deformation speed, or actually the so-called strain rate of the test. The specimen typically has a dog bone shape to confine deformation at its central region, and therefore reduce the likelihood of fracturing at the clamp level. For simplicity, we are going to consider a cylindrical specimen in this video, with an initial cross-sectional area defined by H0 and an initial length, also called gauge length, L0. So we pull it up and stretch it until it breaks. Now, when we stretch a body, it becomes longer along the loading direction and thinner in the perpendicular direction to the load. If we stop the test at any instant, we can measure the current or instantaneous cross-sectional area, AI, and the total length, which is given by the sum of the initial length and the displacement, delta L. The output of the tensile test is typically load and displacement. These two measures are recorded with a load cell. Let's assume we have performed the test on a specimen having an initial diameter D0 of 12.8 millimeters and an initial length of 50.8 millimeters. And then we have got these results. So the force is measured in newtons and the displacement in millimeters. You can find this data in the reference I provided you with in this slide. Now, we have a question now. We have force and displacement, so why do we need to have or calculate stress and strain? The answer is simple. Force displacement characteristics depend on the specimen size. Now, to minimize these geometrical factors, these measures are normalized. And then we have engineering stress, sigma eng, and engineering strain, epsilon eng. The engineering stress is defined as the force divided by the initial cross-sectional area of the specimen. And this latter can be calculated from the initial diameter of the specimen, and the units of your engineering stress is megapascals, since 1 megapascal is equal to 1 newton per millimeter square. The engineering strain, epsilon eng, basically quantifies the change in length of the body in relation to its original length. Clearly, this measure is unitless. Now, so far, so good. However, there is a problem here. We can notice that in the engineering stress calculation, we use the initial cross-sectional area, but we say that it decreases during the test. So for this reason, we make use of true stress and true strain. Now, assuming that the volume of the specimen doesn't change, so basically it remains constant, we can write the true measures in function of the engineering ones. And said so, the true stress is given by the product between the engineering stress and 1 plus the engineering strain, while the true strain is the natural logarithm of 1 plus the engineering strain. So we can see that these two formulas share one common factor, which is 1 plus the engineering strain. So with these formulas, we can obtain the engineering and true stress-strain curves. Now, during the test, the material goes through various stages. So let's say we start stretching the material, and in the first stage, it deforms elastically up to a point identified by the yield point. So the position on this point is difficult to measure precisely. We will see in the next video how this can be done. So this point basically indicates the yield strength of the material. So at this stage, we have the so-called yielding phenomenon, where plastic deformations begin. So plastic deformations are basically deformations that are irreversible. After yielding, the stress necessary to continue plastic deformation in metals increases to a maximum point or value called ultimate strength, which is identified with sigma u here. This corresponds to the maximum stress that can be sustained by a structure in tension, and if this stress is applied and then maintained, fracture will result. Then the stress decreases up to the failure of fracture strength, labeled as with sigma f here. And basically here, it's the point where the material breaks. Here are reported the values I calculated for each of these mechanical properties or material properties. And in the next video, I'm going to show how to calculate these points by using a simple Python script. And if you liked this video, please subscribe. I hope you enjoyed it, and I will see you in the next video. Bye.